development for iodine analysis, the development of a gas hole detector, a detection kit, methods for quality control of gas hole, and contact address, department or school chemistry, and email. Maybe you can read further from his from the department. I mean from the department. Okay. Before presentation, as the opening speech, please Mr. Adi Darmawan as the Chief Editor of JKSA to give opening speech. Please, Mr. Adi Darmawan.
Okay, thank you, Pak Gunawan. Good morning, everyone. Good morning, especially for the Professor Dr. 𝐉𝐊𝐒𝐾t. Sorry if my pronunciation is not good. Okay. Thank you for coming to our 8th webinar. Actually, we have a webinar series which is organized in March. So every second Wednesday every month, and now we have the 8th webinar. Actually, we have 8 speaker before, 7 from Australia, from India, from Malaysia, from Japan, and also from Singapore. So I will try to organize the speaker from different countries. Yeah. Also one from UK, and today the speaker is from Thailand. Yeah, from the 𝐉𝐊𝐾t University, which is I think the first ranked university in Thailand. Yeah. Actually, I already met Professor 𝐉𝐿𝐾𝐻 in conference in IC2MS in 2017 when she presented, and I actually this webinar this month will be presented by the one speaker from US, but she contacted me a few days ago, and she said that she can't to give a lecture on this month, so she asked me to shift to next month, to April, and I asked Professor 𝐉𝐿𝐾𝐻 to give a lecture in this month. So thank you very much, Professor 𝐉𝐿𝐾𝐻, and for everyone, please enjoy this webinar, and I hope this webinar also can make another future collaboration between we are in Undip to 𝐉𝐊𝐾𝐻 University. Thank you. Good morning.
Okay, thank you, Bati. And as the main program in our webinar today, please Mr. 𝐷𝐿𝐾𝐻 to give your presentation around 40 minutes. And after that, we will have question and answer for 15 until 20 minutes. Please, for all participants who wants to give question, write your question in chat room. Please, this is 𝐷𝐿𝐾𝐻.
Okay, so I start now.
Okay.
Yes.
Thank you very much for your very kind introduction, Dr. Gunawan, Dr. Adi Darmawan. Selamat pagi, correct?
Selamat pagi.
Okay, good morning, everyone. Okay, so yes, it's a very good opportunity that one of your speakers has canceled. So I replaced the talk for this morning from Bangkok, Thailand. Okay. Well, I just looked in the Google and see how far apart we are. So if we can have a direct flight from Faculty of Science, 𝐉𝐊𝐾𝐻 University, Bangkok, where my campus is. Oh, I can see Professor Adam from Malang. Aki, okay, fly. So it is 18 hours flight to your university, Diponegoro University. I haven't been there, but I have been to some university that was in basic Science Conference in Malang, I think, in 2015, and again the same year, in November, with my students, and then those are some professors who organized the conference. Sabarudin, Lukman, Rulini in the middle. And in 2015, I went to Medan, I think, Professor Agusna, right? And others, Sasanka, Professor Sasanka, and Adam again. And Hermin, Sulistyati, Rulini, Professor Suyanta in Yogya, Sukirato, and then Dean next. Let me change. Okay. And again, I gave a virtual talk through a virtual conference very recently, last year, end of last year. Okay, let me introduce about Mahidol University. We have about at least six campuses, and I am locating in this small campus Faculty of Science in Bangkok. Okay, the main campus is about 26 kilometers from our campus. That is one of the newest buildings in Salaya, which is the main campus, where we have some concerts and some graduation ceremonies and some important ceremonies of our universities. And you can see the atmosphere. Okay, let's now academic. Okay, let's first have a look at the title of my talk. I believe that there are some students here, so I will try to go maybe slowly. Okay. Look at the name. Contactless conductivity detector. By its name, it's showing you something that it is a detector that doesn't get in contact to the sample, okay? And then I will apply the sensor or the detector for paper-based analytical systems. We will show you 3 systems today. These are figures to give you idea of how the detector looks like. Okay, on the left-hand side is the original, one of the original design of contactless conductivity detector, suitable for detection of conductivity that flows or just be static inside the tube. Okay, it is a non-conducting material tube, such as glass, plastic tube, and then you have 2 pieces of electrode bands. So these are usually made of metals. So when they presented, they have 2 pieces of metal, not in contact, okay? Just placed close to one another, maybe with the 1 millimeter gap or 0.5 millimeter gap or 2 millimeter gaps, it depends. And then you feed in a current, which is an AC current, onto the left-hand side electrode, and you pick up the signal from the second electrode. Okay, you measure the actually you want to see how the current from the original changes at the second electrode. Okay, I'll go into detail, right? And on the right-hand side, it is the configuration of our detector, which is different to the original one. before I go into the topic of contactless conductivity, which is a bit unusual, let's see those conventional conductivity probes, which requires direct contact between the electrodes and the solution. So if you see here, you can see that they usually designed to have two parallel electrodes being immersed into the sample solution. So the electrodes must be in direct contact to the liquid sample. And then you have quite a similar design in electronics to feed in the sinusoidal wave of current on the left-hand side electrode, and then pick up the signal from the opposite electrode. And because the electrodes must be in contact with the solution, so you cannot use like low-cost metals as electrodes. So usually platinum, which is expensive, is used for electrodes. However, if you are thinking of using this electrode in capillary, like if you have to place the electrodes inside a very small capillary, usually capillary will have a diameter of 200 microns, 100 microns. It is not suitable for miniaturization with this concept. So contactless conductivity detector is the solution, is the choice as detector for such the technique. Usually we have several terms for calling this detector, okay? Contactless conductivity detector is one, or capacitively coupled contactless conductivity detector, or C4D, oscillometric detector, and admittance detector. So these are the same thing. Okay, for capillary electrophoresis, okay, for the students who are not familiar with capillary electrophoresis, so, okay, if you may have to imagine a little bit. If you look on the right bottom here, you will see a tube, okay? It's a brown tube. That is the size of a capillary. You can hold it, and then capillary offers separation of your analytes. Say, for example, you have a mixture of compounds. You somehow introduce into a capillary, and then you apply potential across the two ends of the capillary, and then get the mobile liquid to move towards the applied potential. You are able to separate neutral compounds and then a positive charge out of the negative charge compounds. And then everything will float onto one side. Okay, that is a rough principle. Okay, and then you have a detector. Usually they will have a detector like after you separating compound into capillary tube, one compound should reach your detector. Usually they use absorption detector such as UV or visible detector, mostly UV or fluorescence. So both those detectors which are suitable for capillary electrophoresis are optical detectors. However, sometimes your compounds conduct electricity but do not exhibit any optical properties. It doesn't absorb light, so you must find alternative detectors such as maybe amperometry, electrochemistry, and conductivity. Okay, so as I mentioned earlier, that it is difficult to incorporate platinum electrodes inside the capillary column. So you have to you need a sophisticated technique to do that. So let's look what a contactless conductivity detector or C4D offers for you. C4D was first presented in 1998 for capillary electrophoresis or CE. Okay, by two different groups. Okay, they published in Analytical Chemistry Journal in the same year, one following the other. And C4D is now a common detector for capillary electrophoresis. And this is the recent review of C4D with axial electrode. Axial electrodes is the example that I will show you. I showed you earlier. You have a left-hand side band electrode and the right-hand side band electrode put close together. That is an axial design, okay? And the axial designs have been commercialized by this company, okay? It looks like this photographs. So you can slide the detector through the capillary column. So if you have a capillary electrophoresis instrument set up already with UV detector, you can also buy a commercial detector and put it at the end. Just clamp on the capillary, and then you get dual detector. You have the second detector. So if your analyte doesn't show any light absorption property, then you can measure conductivity. Okay, so you have another option. This is the axial design of electrode. Okay, so what C4D does? C4D is a detector that follows change in conductivity of the solution inside the tube. C4D electrodes are contactless. As you can see that the electrodes are placed at the outside. They are placed at the exterior of the tube. So the electrodes are not in contact with the measuring solution. C4D electrodes are usually built in axial configuration. Let's look at a diagram here, see how it works, because actually the electrodes are outside, but the measuring solution flows inside. How it works. Okay, so let's have a look at the cross-sectional view here. If we have a cross-section here, you can see that we feed in the alternating current on the activator electrode, and then we pick up the signal from the second electrode here, okay? So we will monitor the change in current at the second electrode. And these electrical components are just to change the current signal and amplify, change it into voltage signal, which is more common to measure and then amplify, and then you can use a digital multimeter to measure the voltage. Right, let's have a look at an equivalent circuit, which is commonly used to explain why the current at the output of the second electrode is related to the conductivity of the solution, which is not in direct contact to these electrodes. At the cross-sectional view, the yellow circle represents the material of, for example, if you look at a CE uses glass capillary. So this yellow circle representing glass, which is a non-conduct, it doesn't conduct electricity, okay? So it is classified as a dielectric material. And at the outside, on the electrode, you feed in some charge. So with alternating current, let's have a look at one moment in time. You feed in positive charge. On the right-hand side electrode, then you are feeding in at the same time the negative charge. Okay, let's look inside the tube. In a solution containing electrolytes, as well as your measuring compound, okay? If you have electrolytes, you have some negative charge electrolyte, positive charge electrolyte. If you are feeding a positive charge at the outside, at your electrode, it will attract opposite charge species in the solution to move towards the wall, closer to the wall. And in this behavior, it is equivalent to a capacitor. So it becomes a pseudo capacitor at the wall. So this is dielectric, and just look on the left-hand side. This is dielectric material in between two parallel electrodes, okay? So when you consider something like this, you will get some pseudo capacitor form on the wall, such as CW1 capacitor on the wall, and also CW2 for the area of the pickup electrode. We also have another capacitance here, CS. S stands for stray capacitance, okay? So the stray capacitance is you obtain from, it's a similar behavior. You have here the dielectric material, and then you have two metallic bands. So it forms capacitance. It is called stray capacitance. Now let's have a look inside. Inside you have resistance of the solution, as well as the capacitance of the solution inside the tube. When you have all the pseudo electrical component form, like in this equivalent circuit, when you look at it, these are all impedance parameter. And because you are feeding in a constant potential from the alternating current, so the V input, the voltage input is constant, okay? And all the capacitance of these C1, CW2, C solution is negligible because you are measuring conductivity of electrolyte. So capacitance very low. The resistance will play a role. C stray is also constant, right? So you will finally get a relationship between the current at the output electrode is equivalent to the voltage applied at the actuator electrode multiplied by the conductivity. So current is directly proportional to the conductivity. But as I said before, measuring current is difficult. So they have to use some other electrical components to rectify it, to change into voltage, and then amplify the signal before feeding into the digital multimeter. Okay, so that is the principle, how it is related to the conductivity. The signal relates to conductivity. These are just to show you the electrode configuration for tube, okay? In this work, we are interested in planar electrodes. Actually, planar electrodes is suitable for flat bottom channel, such as microchip capillary electrophoresis, because when you build microchip, you have flat bottom channel. So flat bottom channel, if it sits onto planar C4D electrodes, it picks up signals better. This work, we produced flat electrode here. These are our electrodes. So this is the actuator electrode, or called E1, and this is the pickup electrode E2. Okay, produced from printed circuit board. With the technology it is a common technology to produce circuitry using printed circuit board or PCB. Here we only use printed circuit board to etch to etch out a pattern, and we only need 2 electrodes. This time the electrode is flat, okay, and thin, okay, and there is an overlapping area of the electrode like this, which is a 4 millimeter area, and then finally we must not forget that the electrodes, now electrodes becomes very cheap now, and you have to put plastic sheet over the electrode to protect corrosion and protect direct contact with the sample. Okay. Okay, like this. And then you get a planar C4D. This work, we work very closely with our friend in Switzerland, Professor in University of Basel, Peter Hauser. Okay. My computer is slow, so I'm sorry. I have to wait a minute. Okay. Okay, please wait. Hang on, I'm having a problem here. Okay, right. So I think I mustn't use the laser pointer because it makes the slide very slow. Still slow. Okay. This talk will show you the 3 sets of experiment. First, we will show you the C4D, which for using with paper strip for measuring conductivity of a solution. And then we measure and detection of the gas. And finally, with microfluidic paper-based analytical devices and micropad. Let's have a look at the first experiment. At the first experiment, you'll see 2 results of the experiment, A and B. Okay, let's look at the right-hand side first. This is the method that we are proposing. So you have a C4D with the electrodes covering with a plastic sheet as an insulator. Okay. You place a dry paper strip, which is filter paper, cut into the optimum size. Okay, I'll show you later. And then we'll drop the liquid that you want to measure the conductivity onto the paper strip, comparing with when you load the same amount of liquid, the same liquid directly on the sensing area. You can see that we have the same trend between direct loading without using the paper strip, comparing with the paper strip, okay, you can see that paper helps to reduce the size of the error bar. The error bar is representing the precision. So the wider, the poorer the precision. So you're getting a better precision when you use the paper as a sample reservoir to hold and fix the liquid sample in place, as well as controlling reproducible sample shape while you are measuring on the C4D. From this experiment, we observed 2 linear calibration ranges from the sensor, okay? So you can use this first range, the low concentration range of KCl and high concentration range of KCl. We have converted and calibrated the KCl with conductivity probe, and then we have this plot, okay? So on the x-axis, it represents you the conductivity of the standard KCl solution. We also have looked at the pattern. These are 3 patterns that we have evaluated. These 2 patterns, we found that these patterns are not quite suitable because, as you can see, that we have electrode in parallel to one another, very close. So you have a high stray capacitance. Remember CS? We don't want CS to be too high because otherwise you have like a mountain to cover all the signal of your analyte. So we try avoiding that. So we chose the so-called anti-parallel pattern for this work. And this is the application. We just want to show the application to see whether it works or not. And luckily, I think we found an interesting phenomena that, okay, for measuring soil conductivity, usually with soil conductivity, it represents nutrients and salinity of soil, whether it's suitable for some kind of plants or not. Okay, step 1, very simple. Place a dry paper strip on the sensing area, and then we draw 100 microliter of soil suspension. As the suspension, no need to separate. Put the suspension onto the paper strip and read the signal. There is no need to filter out all the dirt of or the soil out of the sample. Just load directly onto the paper, and then you get the signal. So, because filter paper will also filter out some of the soil particle and helps you to measure conductivity directly without sample treatment, unlike the conventional electrode. With the conventional electrode, if you look at this tube, you have to filter until you get clear solution, and then you immerse the conductivity probe to measure the signal. Anyway, when we compare with our method, this is our method, and this is the conductivity probe method, and we use a Z-score to evaluate. You can see that the conductivity probe cannot tolerate the soil suspension because these bars, the blue bars, are outside the dotted lines area. Unlike our sensor, because the way we design it, you get better result. It can tolerate up to 6,000 NTU is the unit representing the turbidity of the solution. So very convenient. How we clean it? After use with soil, you remove the sample reservoir or the paper, remove it, and then use a moist tissue to wipe out all the dirt, following by dry tissue, and then it is ready for the next measurement. You can find further detail in this publication last year, 2020. Okay, let's move to the second work. The same type of C4D. Now we want to see whether it can detect gas absorption and measure something relating to the gas absorption or not. So we have a chamber that looks like this. This is the lid of the chamber made of perspex. And then this is the base. We fit the C4D into this socket and then connect with the electrical component similar to the first experiment. And okay. And here we put a container containing calcium carbonate as solid calcium carbonate. And then this is C4D with a dry paper strip. Close the lid, okay? And now why we are using these compounds? Because we are going to add acid. When you add acid, you get this chemistry. Calcium carbonate, very simple. You are generating CO2 gas, okay? From this container, the CO2 gas will diffuse inside this chamber. And of course, some of the CO2 gas will be absorbed into the moisture. If you load a moisture into the paper strip, okay, or deionized water, then you get this second reaction. CO2 gas, after absorbing into the moisture trapped inside the paper strip, okay, sitting on C4D, you are generating these two ionic species. So it changes the conductivity of the moisture, and we can detect the signal change. Okay, dry paper, baseline of dry paper. After you load just deionized water, the signal increases. And after you leave it, this gas generation and absorption to occur. And then you have this species, you are able to detect the increase of the conductivity signal. And you use that increase of the conductivity signal to plot against the concentration of carbonate in the little vial. So actually, if you look back, we are measuring the signal here, which is related to the concentration in another container, okay? And this graph just shows you two graphs overlay nicely to one another. It shows that you can use powder, and you can also use homogeneous solution for this experiment. Gives you the same result, okay? And we proposed the model that what happened was, first step, there was a diffusion of CO2 from this vial, and then absorption of the gas into the moist paper. The dissolution of CO2 in the moist paper will give you this ionic species, and the ionic species diffuses, okay, diffuses from the top layer, diffuses toward the insulating layer and form a pseudo capacitor, and it becomes, look at the bottom, it becomes a pseudo capacitor on the wall, or called C-wall, on at the feed-in electrode and the output electrode again. So, and we have checked with, I forget the name of the program, that the model will give, it confirms that this model, we have, I think we have checked 3 models, and this model is close to the, it can explain our phenomena. So as you can see here, that all other components are constants except the R solution, which is the resistance of the solution occurring from the dissolution product, proton and bicarbonate. It gives you the change in the conductivity. Okay, so this work, you can find more detail that, okay, how we can use C4D with moist paper as absorbent for in situ detection of the generated carbon dioxide gas, okay? And this is the last one. Similar concept, but we use it with microfluidic paper base. Okay, with the microfluidic paper base, actually it's instead of, we use paper base that look like this, okay? These are photographs of the two sides. This is the acceptor side and donor side. So we have 3 layers of paper. And then in the middle is the spacer, which is the mounting tape with a hole. So the concept we proposed for colorimetric detection in 2016 is we generate gas in the donor layer, and then the gas will diffuse through a hole and dissolve to react with a coloring agent loaded in the acceptor layer, and it changes the color of the reagent like this. So at that time, we had to use a color forming reagent to incorporate, okay? But this time, we use the same concept, but we use it with our PCB C4D. These are just to show you the fabrication of the micropad or the paper device from screen printing, just like your t-shirt, okay? So if you look at the exploded view, we put, this time we flip it over, the gas absorption is put facing down onto the sensing area of C4D. So here we're generating the gas from the top layer, and then we have a transparent tape to put over, and then we get the gas to diffuse, and then get the signal, okay? This is the reaction, okay? Sulphite, actually we incorporate the acid in this reservoir, and then we flow the sample containing sulphite. Sulphite is a preservative. So sulphite will flow from the left-hand side reservoir into the acid to react to generate SO2. After generating SO2, SO2 will diffuse and dissolve into water. Here, we don't need any chemical reagent. We need only water, deionized water. And with this second chemical reaction in the bottom layer, you are generating conducting species that will result in the change in the signal at the C4D. Okay, I have a short clip, 2 or 3 minutes. Let's see how it works. This is the operating procedure for sulphite analysis by using the micropad with C4D detection. Deionized water is dispensed onto the detection zone. Turn over the device and place on the C4D sensor. The signal of water is recorded for 60 seconds to collect the baseline. Sample is loaded onto sample zone, and we see an immediate change in the signal. Inside micropad, sulfite is converted to sulfur dioxide gas by acidification. The gas diffuses to the detector zone through the head space. In process 4, these two ionic species are produced, leading to the increase in the signal. Here is the equivalent circuit for explaining the observed detection phenomena. The signal continues to rise, approaching a plateau value. The readout at 3 minutes is used for the quantitation. For the next analysis, the micropad is removed and disposed. Cleaning is easy. The sensor is wiped using moist tissue paper followed by dry paper. The sensor is then ready for the next analysis. Thank you for your attention. Okay, so I have to go back to my slide. A few more. Okay, so, oh, click doesn't go. I think it's getting slower. I don't know why. Share. Okay. So I think the video clip already explained all these slides. So I will skip this just to show you that we have successfully applied the to determine the preservative in some complex samples such as juice and wines. Okay, so the sample is directly loaded onto the device, and then you throw the device away. Okay, this work is under revision of a journal. So in conclusions, we have shown that PCB-C4D is suitable for paper-based analytical system, and it acts as the paper acts as a sample reservoir to improve the precision of the measurement. And it is the first time that gas detection was carried out on C4D in real time for both the experiment with the chamber as well as the micropad. And we have just showed you the most rapid and convenient micropad method for determination of sulfite. I would like to thank my team, everyone, and all the grants. Thank you, my first lab member. And thank you also goes to all friends and colleagues. You can see that there are some people from Indonesia came to join us at the Mahidol University at an international symposium in 2018. That was just before when we organized an one day before international conference. There was an international symposium for students. And of course, I have been having chances to have some Indonesian students. Welcome more. So this is our current student, Kurnia, ex-student Afi, who's now working at the Royal Thai Embassy in Jakarta, co-advised 𝐷𝐿𝐼𝐻, and now Aulia is studying a PhD in chemistry with another professor in our department. Okay, wish everyone to stay safe from COVID, be healthy. And I really do miss missing friends and traveling to Indonesia. That photo was taken in Medan. Matur nuwun.
Okay. Okay, thank you for your presentation, Ms. 𝐷𝐿𝐼𝐻.
Sorry, yeah.
That's nice discussion about nice presentation actually for your.
Thank you.
Actually, we have 3 questions for this presentation.
Yes.
From Putu. Yeah, from Putu, yeah. what is the type of dielectric material used in planar for CD? Or is that something like Teflon? Yeah, what is it? Nafion? Yeah.
It's a plastic tape. Yeah, I forgot the type. Maybe, well, if I have student here who is working on this, you can help me. You mean the plastic sheet that we put to
Yeah.
cover the electrode?
Yeah, yeah.
Yeah.
Is it like Nafion something?
No. Just actually you can put transparent tape, just like stationery in stationery shop. You put it.
I see.
Yes. Yeah, I can see there are a lot of comments, but many, huh? I try to read.
It is with a more accurate reading result between paper-based detector and conventional probe.
It seems to be. It seems to be because as I showed you in the first experiment with soil suspension, if you have soil particles, you will have a lot of error in detection using conventional probe. But in our system, because we are using not only the non-contact electrode, but also with paper as a sample reservoir, and it also filters out the soil particles, and it doesn't get interfere in our measurement. And you can see that the precision is very good.
Yeah. Okay. Next, buddy. How is the stability of the planar C4D?
Usually we have to, well, as I said earlier, I'm not sure whether everyone was here. We usually turn on the electronic components for about half an hour before carrying the experiment. The stability, now we have been using the sensing head, you know, the flat, the C4D for about 2 years. The same one.
Yeah.
No, stability is guaranteed for at least 2 years.
Okay.
Should be more, because with the principle of a printed circuit board, you can use it for several years.
Yeah. Maybe the other question, I am interested with this system. How about the stability of this detector paper while the conductivity still perform in good condition?
Sorry? Yeah, sorry.
How about the stability of this detector paper?
Oh, paper, you throw it away. It is a disposable. Yeah. So first sample, yeah, one of the reason we try to introduce use with the paper, because paper is very cheap, and it also helps with other properties, improving in the precision of the measurement, hold and fix the liquid sample in place, fix the shape for precise measurement every time. So after use, you remove the piece of paper, throw it away, wipe out, and then put another piece of paper device, and then continue for the next analysis.
Okay, next, Vati. This is maybe from Tamasat. Yeah. What kind of paper strip can be used for this testing? Is a different type for solution and case testing?
I didn't get the question again.
What kind of paper strip can be used for this testing? Is it different for solution and case?
Okay. Yeah. We can use filter paper. Usually in our lab, we tried Whatman number 4. You can also use Whatman number 1, or you can use tissue paper.
No, tissue paper.
Yeah. But
Okay.
tissue paper, difficult because it's very thin, so it doesn't contain so much liquid. So you need a very small amount of liquid. So you will have problem with the imprecision in transferring from micropipette. That's why we don't use. And I have tested with cloth. You can also use cloth as well, but for paper, it is better to destroy after use.
Okay. Okay, next, buddy. How to manage selectivity for non-volatile sample?
Huh?
How to manage selectivity for non-volatile sample?
I'm not sure whether I get it right, but I try to answer. Okay. Okay. When you are using this detector to detect the gas, because we are generating the gas from another layer, so from the sample layer. So in this case, we do not have to worry about the sample matrix because you are measuring the gas in the other layer, okay? Because the gas will have to travel to a headspace, the middle, the hole. So it helps with to avoid interference from sample matrix.
Okay.
I'm not sure whether I got the question correctly.
Okay, next, buddy. This is, thank you for your really nice presentation. I was wondering when you apply alternating current as the input signal for your sensor and change the frequency, is there any effect to the voltage output? I mean the effect of alternating current as the input, and is there any effect to the voltage of the output? Maybe in your presentation.
Yes, I'm trying to. If we applied what can interfere at the output electrode, right?
Yeah.
Okay. During the measurement, do not put the hand on the second electrode because everything will affect the signal at the electrode. So only once, like I showed you in the video clip, when you put the paper device, either paper strip or micropad, just leave it and then do not touch the, okay, I show you here. Oh. Okay, maybe this figure will okay. So just leave it there. Do not touch this because otherwise it will interfere with the applying of the voltage and the pickup of the signal from your finger.
Yeah.
So you have like a spike peak during the recording of the signal. But you just ignore the spike if you just if you unintendedly doing it.
Okay. Maybe the last question is from Thammasat University.
Oh, okay. Thammasat University.
Is there any calibration test?
Again, please.
Sorry. This one, I will.
Again, please.
Okay, I will read. Is there any calibration test that must to do before using to analyze of conductivity properties for quality measurement? I don't know.
Yes. We every time we have to prove with construction of calibration graphs. Yeah, for each part of the work. Yeah, as shown earlier.
Okay, that's all, Patty. I still wonder about the material that covering the electrode. You said it is not like naphthalene. So you put the sample by opening the plastic.
No, no. Something like this is okay.
Oh yeah, I know that.
Okay.
And
but
you
larger.
yeah.
Use larger size. You can buy like an A4 size.
Yeah.
Okay.
And how can the solution immerse?
I'm sorry.
Can the solution immerse to the electrode if you covered with the plastic?
No contact.
Oh, no contact. Yeah. Okay. Okay, I think
masih ada beberapa pertanyaan Pak Gun di layar.
Oke, mana?
Yes.
Ini sudah, Pak.
Ini masih ada pertanyaan.
Oke, terusnya sesudah ini. Ini sudah, Pak.
Okay.
From Professor Rahmania, my field analytical chemistry. I have question. In this system, the paper as stationary phase and combined with conductivity detector for analysis qualitative and quantitative.
I have question.
What is the question? I don't know.
The paper as stationary phase and combine. I just noticed that the question can be read from here.
Yeah.
So many questions.
What is the question actually, Pating?
Huh? Maybe like this. Just okay. Instead of using container like beaker or test tube or tubing, just look at the paper as a sample reservoir, a sample container. Simply speaking.
In the system, the paper as
Is that right?
I don't know. Maybe Rahmania can give a exact question.
I have question in this system. The paper as stationary phase. Yes. Well, yes. Stationary. Yeah. It doesn't move.
Oh yeah.
Applied it for quantitative. Qualitative may be possible, but if you do quantitative, you can qualitative. You have to know what you are measuring first, and then you have to select the right chemistry to convert non-volatile analyte, in this case carbonate or sulfite. You convert it into gas.
Okay, that's all, Buddy.
Okay, yeah.
Okay, I think that's all the question from the audience. Mrs. 𝐷𝐼𝐻𝐻 and after this, maybe if you have a question, maybe you can send your paper your question directly to Mrs. 𝐷𝐼𝐻𝐻 by email, maybe.
Yes, I'm now typing my email and my Facebook in the chat. @gmail.com. I usually use the Gmail one. Now I just type in the email contact. If someone or anyone are interested, please write to me. Also, Facebook. Facebook, I use 𝐷𝐼𝐻𝐻 First Labs.
Okay.
Oh. Yes, I saw messages from friends from Malang. I saw Rulini's message and Hermin. Thank you very much.
Yeah.
I may miss because many messages. Thank you. Lovely.
Okay, I think the time is up for today's discussion. Thank you for your coming to this webinar. This is 𝐷𝐿𝐻𝐚𝐥 𝐊𝐢𝐻𝐚, and I hope we will have another time. We can have another discussion maybe, and also the cooperation between our university. Maybe we can make a.
Oh, you're welcome. Shall we have a group photo?
Okay.
But we need
you.
I also say thank you for all participants in this webinar. Thank you for your coming, and I hope you will stay healthy and have a nice day for today. And I stop this seminar for this time. Thank you once again, Mrs. Nakrapicha.
Oh, matur nuwun.
Okay, matur nuwun.
Thank you very much for the coming, and for the all support. Well, I just remind that our webinar will be held every month, every second Wednesday every month, and for the next speaker will be Professor Alexander from the University of Washington. So stay tuned with our webinar at 9 p.m. So see you in next month. Yeah. For the Professor 𝐷𝐿𝐻𝐚𝐥, thank you very much for your nice presentation today. And keep in touch. So I maybe next time I will contact you. Thank you very much.
Tadi sepertinya profesornya minta foto bersama. Mungkin untuk dokumentasi beliau.
Oke, thank you. Buat semuanya, monggo silakan dibuka videonya, monggo.
Dia pencariannya jalan keluar, pindah hari Sabtu. Hari Sabtu bisanya. Hari Sabtu tuh Bu Olikonya, ndak pun dia pindah-pindah.
Okay, for everyone, just open your video, your cam, so we can take a picture for everyone.
Oh, if my students are here, you can help having the. You can please send me the photo. Yeah.
Okay, 1, 2, 3, and for the gallery view. Okay, 1, 2, 3. Okay, next, because we have a lot of at least 4 pages.
I know. Difficult.
Okay. And next one, 1, 2, 3. Next one. Okay, 1, 2, 3. Wait for the last one. Okay, thank you. 1, 2, 3. Okay, this one. Yeah. Okay. Okay, that's all. Thank you very much for your coming, and see you next month. Okay.
You're welcome.
See you.
Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
See you. Bye-bye.
Nice lecture, Juang Dai.